mechanical weaving loom is the exact starting point of modern manufacturing. It sparked the first industrial revolution, pulling textiles out of homes and centralizing them into massive production facilities. Today, the textile and apparel sector is an economic giant, driving huge portions of global GDP. Yet, despite this massive scale, many facilities remain dangerously tethered to their historical roots. The sector struggles with inefficiency, generating high levels of waste while relying on dense physical labor that cannot scale to meet modern global demand. In an environment where consumer trends shift in days, these slow response times lead to market irrelevance. History shows that even market leaders, like Nokia or Kodak, can lose their footing entirely when they fail to recognize a necessary technological shift. Textile producers who cannot bring new ideas to market quickly and cost-effectively face that exact same existential threat today.
This chart details the evolution of manufacturing toward Industry 4.0. To survive, the textile sector must move past simple mechanization and adopt cyber-physical systems. This involves integrating the Internet of Things, where machines use real-time data to coordinate and optimize the entire production line. Transforming the industry into an intelligent, zero-waste system requires a total overhaul of the garment lifecycle. Every phase, from the first design sketch to the final delivery, must be rewired to prioritize precision and speed. This flowchart illustrates where production delays begin. The traditional design process involves a slow loop of physical painted copies, woven samples, and manual shipping. If the customer requests a change, the cycle repeats, dragging lead times out for weeks or months. Computer-aided design, or CAD, replaces that physical loop with a digital one. Designers can instantly alter patterns, adjust hues, and secure approval via email. As the diagram shows, this shifts the timeline from months to a window of 24 hours to a few days. Digitizing the dyeing board allows manufacturers to finalize a design before spending a cent on physical materials. It eliminates the need for multiple woven samples, stopping material waste before the first roll of fabric is ever loaded onto a machine. Once the digital design is ready, manufacturers can deploy a digital twin, a virtual model of the production system. This allows them to simulate operations and spot inefficiencies or potential equipment failures in a digital environment before implementation. On the physical factory floor, the transition to Industry 4.0 involves embedding IoT sensors throughout the line. These sensors gather data that enables artificial intelligence to oversee quality control in real time. This schematic maps out an automated fabric inspection system. As fabric moves through the equipment, an array of emitters and detectors scans the material. Machine learning algorithms analyze this data to identify microscopic flaws in texture or dyeing that human inspectors miss. AI intervention stops errors immediately, preventing flawed batches from completing the production cycle. This real-time quality control significantly reduces the volume of unsellable garments that would otherwise end up in landfills. Even with a sustainable production line, brands face a challenge at the point of sale, proving their environmental and ethical claims to the consumer. Blockchain technology provides the solution by creating a secure, unchangeable record of every transaction in the supply chain. It tracks the exact origin of materials, from the farm that produced the cotton to the factory's fair trade certification, creating a permanent digital trail. By turning sustainability assertions into verifiable data, blockchain creates a layer of transparency that helps protect brand integrity. This system builds consumer trust and makes it much more difficult for counterfeit goods or unethical materials to enter the supply chain. While the benefits are clear, the upfront investment costs for these technologies are often overwhelming. For manufacturers in emerging countries, the capital required to build a smart factory acts as a major barrier to adoption. There is also a significant human hurdle. Many workers in the textile sector view new technology with deep apprehension, fearing that automation will lead to widespread job losses. Overcoming this resistance requires a commitment to upskilling programs. Management must transition manual laborers into more technical roles, training them to operate and maintain the very AI and robotic systems that modernize the factory. Upgrading machinery without a corresponding investment in the workforce is ineffective. Comprehensive employee training is a mandatory infrastructure requirement for the modern factory, not an optional benefit. To mitigate financial risk, smaller factories often take a wait-and-see approach.
They monitor how larger, more well-funded organizations adopt specific technologies before committing their own limited resources to the transition. Because the market alone cannot fund this shift quickly enough, government intervention is required. Public policy is necessary to establish the regulatory guidelines and financial frameworks that support large-scale industrial change. Targeted policies, such as tax cuts, monetary grants, and subsidies, can reduce the financial burden of these upgrades. These incentives motivate businesses to install advanced, eco-friendly systems that might otherwise be cost-prohibitive. Sustaining the textile industry requires a combination of advanced technology, upskilled labor, and government backing. This triad is the only way to transform a historically wasteful sector into an efficient manufacturing model capable of meeting global environmental and market